So we've already talked about mutual inductance before in the time domain. And somebody had asked, I don't remember who it was, are we going to solve those? And I told you we weren't going to solve them until we get to the frequency domain, because otherwise you have to solve it using differential equations in the time domain. So by doing it in the frequency domain, we can use phasors, okay? So a transformer uses a matched impedance and eliminates DC signals from a portion of a system in communication systems. It's also used in power systems to establish a voltage level for transmission, distribution, and consumption of electrical power. The easiest way to think about a transformer is it steps up or steps down voltage. So outside of buildings and your home, there's always a step down transformer, right? From the power signal, it might be a higher voltage, and then for them delivering it to your home, they step it down to the appropriate voltage, which is probably 120 volts AC, to come into your home. So that's what transformers do, is they step up and step down power. But you can also use the matched impedance for communication systems. Just like an inductor for mutual inductance, it is made up of coils wound on a single core to ensure magnetic coupling. So think about yesterday when you guys put your metal strips inside the inductors. You got a stronger coupling. So another way to get a stronger coupling is to wrap both of them on the same core, where the number of turns dictates how strong the coupling is. This is that strength of the coupling. If you think about that K, that coefficient you calculated in your lab. So the way we model that transformer here, it looks just like mutual inductance. But when it's an ideal transformer, there will be two vertical lines in it, and you'll see that in a minute. Okay, so we like to say that the source has the primary windings, which is N1, and the load, or the other side, has the secondary winding, which is N2. In a linear system, N1 over N2, which is the number of turns, is proportional to the ratio of the inductance for L1 and L2. And the mutual inductance is defined by the coefficient of coupling, K, times the square root of L1 times L2. Everyone should have written this in their pre-lab. Yes? What pre-lab? We didn't do no pre-lab. I don't know about no stinking pre-lab. Everybody remember the pre-lab? Okay. The coefficient of coupling tells you how strong the connection is for the mutual inductance. So if K is equal to 0, they're not coupled. There's no common flux. If K is equal to 1, it's perfectly coupled, which is the transformer we're going to talk about in a minute. Anything in between is either loosely or tightly coupled. Are there any questions? Okay. Page 2. So the total energy in the mutual inductance is 1/2 L1 I1 squared plus 1/2 L2 I2 squared plus or minus M I1 I2. That's the mutual inductance. And it can have a positive sign if both currents enter or leave the dotted terminals for each inductor, or it has a negative sign if the current enters for one and leaves for the other. An ideal transformer is when K is equal to 1, which is the tightest coupling, of two magnetically coupled coils, and we have N1 and N2 terms that exhibit the following three properties. Notice, like I said, you can tell this is a transformer because it's ideal and it now has those vertical bars there. And also because the M is missing. So the coefficient of coupling is unity. The self-inductance of each coil is assumed to be infinite, or L1 equals L2 equals infinity. And coil losses due to resistance are negligible. Negligible and infinity are modeling. Obviously, they're not exact. It's just really big numbers or really small numbers. There are two characteristics for an ideal transformer. One of them is that V1 over N1 equals V2 over N2. That's absolute value because current could be negative or positive, just like voltage could be negative or positive. The other one is I1 N1 equals I2 N2, where that ratio N can be represented as N2 over N1. Lowercase n represents the ratio N2 over N1, where the primary winding has N1 turns and the secondary winding has N2 turns. So An isolation transformer means it does not step up or step down the voltage. It just has a big impedance between the input and output voltage. That would be N equals 1. N greater than 1 is a step-up transformer. That means I put in a small voltage, I get out a bigger voltage. N between 0 and 1 is a step-down transformer, which means the secondary side has a lower voltage than the primary side. How are we doing so far? Did you guys learn about transformers in one of your other classes? Okay. The conventions for determining the polarity for the currents and voltages on the transformers use the following rules. If the coil voltages are both positive or negative at the dotted terminal, use a plus sign in the voltage relationship, otherwise it's negative. If the coil currents I1 and I2 are both directed into or at the dot marked terminal, use a minus sign in the current relationship, otherwise use a positive. So this graphic shows the 4 possible orientations for that. So up here, both of my voltages are negative at the dot, so this relationship is positive. Over here, both currents are leaving, so the current relationship is negative. This is based upon the rules at the top of the table. Here, one voltage is positive at the dot, the other voltage is negative at the dot, so that relationship is negative. The currents, one goes in, one exits, so the current relationship is positive. Is everybody following me here? The third row of the table. V1 is negative at the dot, V2 is positive at the dot, so that voltage relationship is negative. The current leaves for V1 and it leaves for V2, so the current relationship is negative. And the last possible option is V1 and V2 are both negative at the dot, so the voltage relationship is positive. And I1 exits at the dot, I2 enters at the dot, so the current relationship is positive. So here we have a transformer circuit, and it also has a source voltage with a source impedance and a load. So the input impedance at the primary side is the same as V1 over I1. So the primary side of the inductor is the same as V1 over I1. So that would be equal to 1 over n squared V2 over I2 on the secondary side. How did I get this equation here? It's completely based upon that table, because I have relationships between V1 and I1 and V2 and I2. So that means that if I want to represent the input impedance on the load side of the circuit, it's 1 over n squared times ZL. This works because, remember, if I go back and look over here, let's write down the formulas. They're both positive at the dots, right? So that means that V2 equals N V1, right? One current enters at the dot, one current exits at the dot, so that means that I1 equals N I2. So if I have V1 over I1, I stick this in my formula. And you get V2 over I2 over n squared, right? Does everybody see that? That's where this comes from. But I know that V2 over I2 is the same as the impedance of the load. It's the voltage over the current, which is ZL. So that becomes 1 over n squared ZL. Everybody good? All right. So it is possible to simplify the analysis of a transformer by reflecting the secondary side to the primary side and vice versa just by using these formulas. So for example, I can write this as a simplified circuit by reflecting the secondary to the primary, where the primary values remain the same, but the reflected secondary impedance to the primary side becomes ZL over N squared, which is this formula right here. And the voltage V2 prime equals V2 over N, and I2 prime equals N times I2. The prime just means I'm taking something on the secondary side and reflecting it to the primary side. That's what the prime means. So here's the same circuit that I have up here, except now ZL prime and V2 prime have been simplified to make a loop circuit because it's easier to analyze. Okay, or I can make a loop circuit by going the other way, by reflecting the primary to the secondary side. Now for this one, the secondary remains the same, V2 and ZL, and I use my formula so I can reflect ZS prime and it becomes N squared ZS, and VS prime becomes NVS, or V1 prime becomes NV1, and I1 prime becomes 1 over N I1. And now it's easier to solve because I have a loop equation and I can find voltages and currents and things. Okay, any questions before we do an example of this? All of that was to get you ready for your example. I know the excitement is killing you, but we're ready to do an example now. Ruby said, yeah, that was a long movie preview. I'm ready for the main event. Ruby said, I didn't say any of that. All right, page 5. So a coil with a self-inductance of 150 millihenry is energized with a current of 5 sine 500 T. This causes a second coil to develop an open circuit voltage of V2. Let's try to draw what we have here. Here's our coil with 150 millihenry with a current of 5 sine 500 T in amps. This causes a second coil to develop an open circuit voltage of V2 of T equals 389.7 cosine 500 T volts. If 10% of the developed flux leaks determine the mutual inductance of the pair, I gotta find M. And the self-inductance of coil 2, I gotta find L2. And the maximum energy stored. So first, in the phasor domain, I'm going to have V2 is equal to 387.57 with an angle of 0 degrees. In the phasor domain, V2 is equal to 389.7 with an angle of 0 degrees. Now, because this is an open circuit, the only voltage over here is due to the mutual inductance. So that voltage would be J omega M I1. So this is to be J times 500 times M times I1, and that equals 389.7. Oops, sorry, I meant to put I1 in here. I1 is 5 with an angle of negative 90 degrees. Solve for M. Solve for M. Should be a real number. Sage.
I got 0.156.
Very good. 156 millihenry. Any questions so far? So there's M. That was one thing we had to find. 156 millihenry, sorry. So M is equal to K times the square root of L1 times L2. Since it says 10% of the developed flux leaks, that means I don't have a strong coupling. That means my K is only 0.9 because 10% leaks. We know if K is 1, it's a transformer anyway. So now, can we solve for L2? So I'm going to have M squared equals K squared times L1 times L2. So L2 is equal to M squared over K squared times L1. L2 equals M squared over K squared times L1. What is L2? We know M, we know K, we know L1. What's L2? Peyton? 200 millihenry. 200 millihenry, very good. Are there any questions so far? Any questions? All right, now we need to find the energy. The energy stored in the inductors is 1/2 L1 I1 squared plus 1/2 L2 I2 squared plus or minus M I1 I2. So the maximum, because this is a sine wave, the maximum energy would occur at t equals 0, right? Because a sine wave is maximum at t equals 0, and my current is a sine wave. So for maximum value, I need to find the energy at W of 0. For a sine wave, the current is maximum at time 0, so that would give me my maximum energy. So that's going to be 1/2 times L1, which is 150 milli, times I1, which is 5 squared. It's an open circuit, so I2 is 0 amps. So what is the energy? It's an open circuit, so I2 is 0 amps. So I don't even have to write down the rest of the formula. 1.875 joules. Very good. Any questions? Any questions? Find the following circuit determine the energy stored in a couple inductors at t equal 1.5 seconds. First thing we got to do, as always, is convert this to the frequency domain. The first thing we always have to do is convert this from the time domain to the frequency domain. So the voltage source is 20 angle 0 degrees. That resistor is 4 ohms. The capacitor is negative J over omega C. So the capacitor should be negative J over 2 times 1/8, or negative J4 ohms. The impedance of the capacitor is negative J4 ohms. Then you draw the inductor, show the dot. I'm going to assume clockwise current. And that is going to be 2 times 2. So this inductor is J4 ohms. Oops, I forgot. I got to show the mutual inductance. Sorry about that. It's not 0 because I don't have an open circuit. Okay, I'm going to model the induced voltage as a dependent voltage source. So here is M, that's J2 ohms. Here's the other inductor. That's J2 ohms and 2 ohms. And there's I2. So everything's drawn except for what goes on those diamonds, which represents our induced voltage. So for I2, the current goes in at the dot. So that means the voltage is positive at the bottom and negative on top for the left side. And this is J2I2, the induced voltage. Okay. For I1, the current exits at the dot. That means it is negative at the dot. Negative on the bottom, positive on top. It's been a while, but we did do this in class, I promise. So that one is J2I1. All right, we now are going to write two mesh equations. Write a KVL equation for mesh 1. And then write a KVL equation for mesh 2. We're going to have 4I1 minus J4I1 plus J4I1 minus J2I2 equals 20 angle 0 degrees. 4I1 minus J4I1 plus J4I1 minus J2I2 equals 20 with an angle of 0 degrees. How did we do? KVL is mesh current. KCL is node voltage. These are loops. I would never do node voltage on this. If it looks loopy, KVL. If it looks nodey, KCL. All right, KVL at mesh 2. J2I2 plus 2I2 minus J2I1 equals 0. J2I2 plus 2I2 minus J2I1 equals 0. Okay. What is I1 and what is I2? I'm putting my answers on the dot cam and you confirm whether you get the same answers or not. I'll give it to you in rectangular and polar form. Okay. I1 is 3.846 plus J 0.769 amps. I2 is 1.538 plus J 2.308 amps. Or I1 is 3.92 with an angle of 11.3 degrees. And I2 is 2.77 with an angle of 56 degrees. I1 of T would be equal to 3.92 cosine 2T plus 11.3 degrees, and the units are amps. I2 of T would be equal to 2.77 cosine of 2T plus 56.3 degrees, and the units are amps. And so the question says, what is the energy at T equal 1.5 seconds? What is the energy at T equal 1.5 seconds? So the energy formula is 1/2 L1 I1 of T squared plus 1/2 L2 I2 of T squared, and then it's either a plus or minus M I1 I2. The way we decide is if they both enter or they both leave at the dot, it's positive. Since one exits and one enters, it's a minus M I1 of t, I2 of t. And then at that point, you're plugging and chugging, chugging and plugging. And the answer is 9.59 joules.